All right. Good morning. No, you're fine. You're fine. Section 4.6 is everything that we've been talking about for days and days, finally put together. And yes, these are the problems with parts A through S, which I believe is 19 parts to a problem. And you're going to have 20 of these on the test. I'm kidding. I'm kidding. You cannot possibly have 20 of these on the test. But we're going to use everything that we know about from algebra, about domain and x-intercepts and y-intercepts, and we knew stuff about asymptotes from algebra, and then everything that we've learned about graphs from calculus. So let's talk about what we can determine from a graph by looking at its first derivative. Y'all help me with this. What does it tell you when the first derivative is positive? Function's increasing, and when the first derivative is negative, function is decreasing. Where the function goes from where the derivative goes from increasing. No, let me try one more time. Where the function goes from increasing to decreasing, what does that tell you? Function goes from increasing to decreasing. There's relative max. Where the function goes from decreasing to increasing, there's a relative min. Where the first derivative is where the second derivative is positive, what does that tell you? Upward concavity. And where the second derivative is negative, that tells you downward concavity. And where the second derivative changes signs, either positive to negative or negative to positive, what does that tell you? That's a point of inflection. All right, let's see if we've covered everything in that first paragraph. Where the function is defined, but the derivative is 0 or undefined, that's a critical number, which is a possible relative extrema. We don't know for sure yet whether it is a relative extrema. We got that, we got that, we got that. And we rarely use the second derivative test. All right, so that's a summary of 4.1 to 4.5, all in one paragraph. And then the other things we may need, the definition of a horizontal asymptote is just the horizontal line y equals L if the graph approaches L, if the y values approach L as your x's approach either infinity or negative infinity. And then the guidelines for horizontal asymptotes of rational functions, we talked about those yesterday, so they should be still pretty fresh on your brain. Slant asymptotes are not going to happen in our first few examples, so we'll talk more about them later. We have 3 days to do this. I've got the examples, I've got the homework. I just really spent a lot of time giving you a format that will encompass everything that I want you to give me on each problem. Also, just before I forget, it is time to start the practice test. Raleigh, you asked me when the next test was, and it's next Thursday. So we have 3 days to cover 4.6, and then we have 2 review days, and then test 3 next Thursday. All right, let's start. Yes, ma'am. I'm never going to tell you you have to identify relative extrema using the second derivative. Okay. I'm just going to say identify the relative extrema, and you use whatever you think is convenient to do that. Okay. All right. All right. If everything in life was a polynomial, like calculus would be so easy. So let's start with a polynomial. A 4th degree polynomial with a positive coefficient. What does that tell you about the end behavior of that graph? Both ends go up, just like x to the 4th. So that's just kind of a mental note to keep me aware of what I'm expecting this graph to look like. What's the domain of that function? You can let x be anything in a polynomial. So negative infinity to positive infinity. Remind me how I find y-intercepts. let x be 0, and I can just tell by looking at that, every term with an x in it would be wiped out, and the y-intercept would just be the constant, 5. So I'm going to write these as points, 0, 5. How do I find x-intercepts? Let y equal 0 and solve that equation. Now, the reason that I made this handout 12 pages long is I realized several years ago that if I had to do all of the work in class, I couldn't get very many examples done at all. So I actually spent a day or a week or a year typing all my work that I wanted you to be able to see, but I didn't want to have to spend time doing it in class. So I've corresponded from the C parts. That's where we're looking for the x-intercept. I set it equal to 0, and I prayed that it would factor, but it wouldn't factor using any method that I knew before chapter 5 of college algebra. I had to use the possible rational zeros theorem. I had to find the first number that would make that left-hand side equal 0, and then use synthetic division to get it down into lower and lower degrees. So by substitution, I found out that 1 made that left-hand side equal to 0, and then I did synthetic division with 1 in the box, and that broke the 4th degree equation down into a linear factor times a cubic factor. And then I had to do substitution again to find another 0 of the function. And I found out that 1 is still a 0 of this guy. And that means when I do synthetic division, I get 0 for a remainder. And that gets my 4th degree equation down into x minus 1 times x minus 1 times this trinomial. And then finally, that trinomial will factor using methods that I know. And so I finished factoring it, and I got the 2 x-intercepts, +1 and +5. But that took a long time to do, and I didn't want to do it in class. So my x-intercepts, if I let y be 0, I get x is 1. And if I let y be 0, I get x is 5. What about vertical asymptotes? Polynomial functions don't have asymptotes. So there are no vertical asymptotes and no horizontal asymptotes. We know that both ends are going up, so there's no horizontal asymptote as x goes to infinity and negative infinity. Y is going to positive infinity on both ends. Slant asymptote, we'll talk about those later. They're not probably even going to come up today. First derivative of the function, go ahead and write that down. And then I had to find my critical values. How do I find critical values? What does that even mean? What makes the first derivative 0 or undefined, but yet the function's defined there? Well, the function's defined everywhere, so I don't have to worry about that. Critical values, here's my derivative. Is there anything that makes it undefined? No. So I had to find out what makes it 0. And since that is a 4th degree polynomial, I tried to factor it by grouping. It wouldn't factor by grouping. So I had to go back to the possible rational zeros theorem and find the first thing that made that 0. First thing I found was 1. So I did synthetic division with 1 in the box. And I got that derivative factored finally into 4 times x minus 1 times, or 4 times x minus 1 squared times x minus 4. So what are the critical numbers? 1 and 4. what are the, what's the second derivative of that function? Awesome. And defines critical values for the second derivative. I need to set that equal to 0 and factor it. So I didn't type that word. I'm just going to put it out here and label it. And this is what I want you to do in your homework. When you need to do work on some part, I want you just to come out to the side, label, hey, here's my work on part C, here's my work on part H, here's my work on part I. When I set 12x squared minus 48x plus 36 equal to 0. So as critical numbers for the second derivative, I got 1 and 3. Okay. All right. I'm going to put everything I need to know about the first derivative and second derivative on one sign chart. And on that sign chart, if the domain has any restrictions, I'll make a note of that. If there are any discontinuities, I'll make a note of that. And then I need my critical values of both the first and the second derivatives. No restrictions on the domain. This function, any polynomial function, goes all the way from negative infinity to infinity with no discontinuities. The critical numbers of both derivatives are 1, 3, and 4. And I need the sign of the derivative in each of those intervals. How many test points do I need? 1 here, 2, 3, just 4. 1, 2, 3, 4 intervals. Okay. So I'm going to get the signs of my first derivative first, and my first derivative in factored form. Where is that? That was part G, first derivative in factored form. Was where I set that equal to 0. And so I'm going to plug my test points into this. That's factored form of the first derivative. When I let x be, well, before you start plugging in numbers, notice that coefficient's positive. What about the first factor? Yeah, it's never going to be negative. So really, all I care about is what's the sign of x minus 4. If I plug in say a 0, what's the sign of x minus 4? Negative. And if I plug in a 2, it's negative. And if I plug in a 3.5, negative. And if I plug in a 5. Okay. The sign of the first derivative only changes at 4. So it's negative up to 4 and then positive after 4. What about sign of the second derivative? Second derivative in factored form is right here. The 12 is positive. I want the value of the second derivative if I plug in a -1. I don't want the value of the second derivative. I want the sign of the second derivative if I plug in a -1. Oh, that would be negative. That would be negative. The negative times a negative is a positive. And then if I plug in a 2, that would be a negative times a positive is a negative. And if I plug in a 3.5, that would be a positive times a positive is a positive. And if I plug in a 5, that would be what? Positive times a positive is a positive. Let me check. Yeah. Yeah, I don't want to say that. What part of that sign chart do I look at to determine the increasing and decreasing intervals of this function? First derivative. So look at this bottom line, sign of the first derivative, and tell me where the function's increasing. Wherever the first derivative is positive, and that would be 4 to infinity. What are the decreasing intervals? Can you just state it like that, negative infinity to 4, or do you need to label each interval separately? Don't erase, just answer the question. There's no discontinuity at 1, 3, and 4, so I can write that interval as just one interval from negative infinity up to 4. So if there were discontinuities, I'd need to skip over them. Looking at the first derivative, how do you identify relative max? I want words, not the answer to what is the relative max, but how do you identify? When the function goes from increasing to decreasing, where the derivative goes from positive to negative. Does that happen? Doesn't happen here. And how do you identify relative minimum? When the function goes from decreasing to increasing, or when the derivative goes from negative to positive. Where is that? 4. And I went ahead and calculated the y for us just to save time. Where did I get that y? Plug the 4 into the original equation, because I'm graphing the function. I'm not graphing the derivatives. All right. How do I answer questions about concavity and points of inflection? Sign of the second derivative. How do I identify the concave up intervals? Where the second derivative is positive. So negative infinity up to 1. The second derivative is positive, and then 3 to infinity. Second derivative is positive. What's the concave down interval for this function? 1 to 3 is where the second derivative is negative. How do I identify points of inflection? So just wherever second derivative changes signs. Where's the first place that the second derivative changes signs? 1. And if I let x be 1, I got y as 0. What's the other place the derivative changes signs? Second derivative changes signs at 3. So my 2 inflection points are 1, 0, and 3, negative 16. Now, how do we put this all on a graph? Which sections actually of A through S, which one actually gives us points that we can graph? B gives us points. C gives us points. O gives us points. And R gives us points. So let's graph all those points. 0, 5 is the y-intercept. 1, 0, and 5, 0 are the x-intercepts. But okay, Ms. Bailey?
Yeah.
Oh, yeah. I spent a long time figuring out the best scales of the graphs to graph these suckers. Because they don't all fit on a standard window. Relative mean at 4, -27, we'll call that about here. Point of inflection at 1, 0, I already have that graphed. And then the other point of inflection 3, -16, all that about here. Actually, so you can see better. And it's, I don't know if I can do red on top of black, but I want those points to show up better. All right. I suggest that you graph and pencil, because you might need to change something about your graph. We have to, I think it's the concavity we'll have to work the hardest on. This graph is supposed to be concave up from -infinity to 1. That's up to this point right here. And we know the graph is increasing on the left end. So can you make that? Well, no, it's pointing up. It's not increasing. It's going downhill from left to right, but the left end is pointing up. Can you make the graph look concave up until 0 or up until 1, 0 and pointing up on the left end? What about 1 to 3? From 1 to 3, I'm looking back at my sign chart and I'm saying, excuse me. The graph is decreasing and it's concave down. Make it look, obviously it's got to be decreasing to get down to this point, but can you make it look concave down? And 1, 0 is a point of inflection. Do you understand why that's concave down? Okay, I might have trouble explaining if you didn't understand, but I don't want to leave anybody if anybody's thinking, why is that what concave down looks like? What about 3 to 4? Again, I'm looking at my sign chart. I'm saying the function's decreasing, but concave up. I'm going to make it look decreasing, but concave up. So that the point 3, -16 looks like a point of inflection where the concavity changes. And then from 4 to 5, the graph is increasing and concave up. Now I'm going to be checking your calculus on the test. I don't want you just turn up with magical, beautiful graphs and no work to support it. I won't give you credit for that. But I can certainly check my graph that on your calculator and use the same window that I did here. Use the window X's from about -1 to 5 and Y's from -30 to +30. Equal to what we came up with. I can check my increasing, decreasing intervals. I can check my y-intercepts, my x-intercepts, my concavity. I can check everything about this problem. And so on the test, and don't hold me to this, I'm telling you what I think I remember, and I haven't made this test yet. I think I remember giving you one problem with all of these parts, but yay, it's just the polynomial. And you're not gonna have to use the rational zeros theorem, that takes too long. It'll just be a polynomial and you answer everything and you can check the graph perfectly on your calculator. The other problem will have irrational answers so that I have to see your calculus. You can't tell me that there's a turning point at pi over 2 and just give me a decimal approximation of it. That's how I can make sure that you're doing the calculus to get the answers, not just using the calculator. All right, I'm not going to bother graphing the rest of these on my calculator. I want you to check them on yours, but it takes me too long to enter something with a mouse. So, any questions about that first example? All right, that took 30 minutes. Number 12. The first thing you want to do on any rational function is factor the numerator and denominator to see if any factors will cancel, because that will affect whether I have vertical asymptotes or holes in the graph. Right? Okay. If that denominator has two factors and neither one will cancel out, then I have two asymptotes. If one of them could have canceled out, then I would have just had a hole in the graph. What's the domain of this function? Everything but what makes the denominator 0, and that's -2 and +2. How do I find y-intercepts? Let x be 0 and I'd get y equals what? -1/4. Why'd that have a question mark at the end? -1/4. What about the x-intercepts? How do you find x-intercepts? Let y be 0, and with a fraction, what makes the whole fraction equal 0 is what? If the numerator is 0. Is there any value that makes that numerator 0? Not any real value, an imaginary value, but we're not graphing imaginary numbers, so we're not going to get any x-intercepts. Okay. No, because if I squared -1, I get +1, and then I have 1 + 1 is 2. All right, what about vertical asymptotes? Make sure that you're giving me the equation of a line, not just numbers. What are the vertical asymptotes? How do you find the vertical asymptotes of a rational function? What? It's what makes the denominator 0, what you cannot let x be. And we've already determined we could not let x be -2 and 2. So there are vertical asymptotes at -2 and 2. But again, make sure you're giving me the equation of a line, not just numbers. How do I determine horizontal asymptotes? What do I look at for a rational function? The degree of the numerator and degree of the denominator. If both have the same degree, then what's the horizontal asymptote? Ratio of the leading coefficients, which is 1. So what's the equation of the horizontal asymptote? Y equals 1. Slant asymptote, we're not going to have today. All right. To save time, I went ahead and found the first derivative and the second derivative. What's the critical value for the first derivative? Why can the critical numbers not include positive 2 and negative 2? Because the function's not defined there. So the only critical number for the first derivative is what? 0. All right, then I found the second derivative. And the critical value for the second derivative would be what? What am I trying to figure out? Is there anything that makes the second derivative 0 or undefined? Well, what makes it undefined also makes the function undefined, so it can't be a critical number. Is there anything that makes the second derivative equal 0? No, this numerator is always going to be positive. So what does no critical values of the second derivative tell me? No inflection points, know where the concavity changes. This is going to be all concave up or all concave down. So my sign chart needs to have the discontinuities, and the only critical number of either derivative is 0. So I'm going to go -2, 0, and 2. Otherwise, the function's defined from negative infinity to positive infinity. And I'm going to look at first the sign of the first derivative in each interval. So here's my first derivatives. What do you know about the sign of the denominator? Always positive. So really, I only care about -10 times my test point. If I let x be -3, what's the sign of the first derivative? Negative times a negative is a positive. Same thing for -1. But if I let x be +1, what's the sign of my first derivative? Negative and +3 would also make the first derivative negative. The sign of the first derivative only changes at 0. What about the sign of the second derivative? Here's the second derivative. What can you tell me about its sign? It's always positive. So what are my increasing intervals? Could I just write that as negative infinity to 0? No, because -2 is a discontinuity. It's a vertical asymptote. I need to write those increasing intervals separately. Negative infinity to -2 and 2 to 0. And it has 2 decreasing intervals from 0 to 2 and from 2 to infinity. What should I be looking at to determine relative extrema? Where the first derivative changes signs. How many times does the first derivative change signs? Only once at 0. The function goes from increasing to decreasing, which means what happens at 0? There's which one? Relative max. 0 and whatever you get when you plug 0 into the function. Well, we already found that's the y-intercept, -1/4. And what about relative minima? There are none. What should I be looking at to determine concavity? Sign of the second derivative. Where's this function concave up? Can I write it negative infinity to infinity? No, I've got to skip over those asymptotes. So negative infinity to -2. Can I write -2 to +2 without breaking that up? Yeah, there's no discontinuity between -2 and 2. zero is not a discontinuity, it's your y-intercept and your relative max. So I can say all the way from -2 to 2, and then from 2 to infinity. Where is it concave down? Yeah. You can say nowhere or none or not applicable. What about points of inflection? None. All right, remember it's the B, C, O, and R parts that give me points. B, C, O didn't give me any, and R didn't give me any. Oh, I only have 1 point out of all of those. N is a point. Yes, well, it's the same point as the y-intercept, so I really only have 1 point to graph. 0, -1/4. What else could I graph to begin with? The asymptotes, yeah. B and E. -2. +2 on my vertical asymptotes, and 1 is my horizontal asymptote. Oh, sorry, you can't see what I'm doing. Oops. All right, I'm going to zoom out a little bit so I can see my sign charts and my graph at the same time. From -infinity to -2, the function's supposed to be increasing and concave up. From forever to the left up to that first vertical asymptote. Can I tell whether the graph is above that horizontal asymptote or below?
I don't understand.
You're up next. That is funny. Huh?
I was told we can see this.
Why can the graph not, well, actually, I can think of 2 reasons the graph can't be below the horizontal up to that first part. That would be concave down. That would also be decreasing, and that would also require another x-intercept over here. And none of that is true. So the graph has to be above the x-axis, or excuse me, above the horizontal asymptote there. What about skipping over to this right part before we do the middle? The right part is supposed to be decreasing and concave up. Can you do that? Is that, could it possibly be below the horizontal? That would be increasing. And there would also have to be another x-intercept over here. So it can't be below the horizontal, it's got to be above. And then from -2 to 0, can you do increasing and concave up? How would you do increasing and concave up? Would this be increasing and concave up right there? That would be increasing and concave down.
Like right before that.
Let's see. Let me look again. -2 to 0, increasing concave up. Why am I having trouble doing the concave up? I'm gonna come back to that.
One square -4 is -3 and the denominator using the given answer.
Oh, so we missed something on our sign chart right here. Oh, because the denominator is cubed, it can give you a negative. So even without having to look at your calculator, your heart and your gut should know when something can't be right. I could not do increasing and concave up in that part. So that was supposed to be anything from -2 to 0. Second derivative. Come on. Double check. -1 would give me a negative in the denominator. And so, yes, that would be negative. And what about, say, -3? -3 would give me a positive because I'd have 9 minus 4 is positive in the denominator. So yeah, there is a concave down. All right, between 0 and 2, if we let x be 1, yes, the numerator is always positive, the denominator would be negative. Gosh darn it. That changes several things. Only the concavity and inflection points. It's concave up from -infinity to -2. It's just not concave up in the middle. It's concave down in the middle, which makes more sense. And then there would be 2 inflection points. Oh, would there be 2 inflection points? The answer is no, but why? The concavity changes at -2 and 2, but those can't be asymptotes because they're, or excuse me, those can't be points of inflection because they're asymptotes. So now I can do concave up and increasing there. Concave down. No, concave down all the way from -2 to 2. Increasing -2 to 0 and decreasing 0 to 2. And then I can check it. All right. Let's tackle number 16. I think it would be easier to tell some things about this function if I combine that into a single rational expression. So if I got a common denominator, wrote that 1 as x squared over x squared, then my single fraction would be 4 plus x squared over x squared. And I can double check that by breaking it back into 2 different terms. First term is 4 over x squared. Second term is x squared over x squared. That's my 1. So the domain of that function is all the values for which the function's defined. That's everything except for what makes that denominator equal 0. And that would be x is 0. The domain is everything but 0. The y-intercept. What do you know about the y-intercept? If you can't let x be 0, then there's not going to be any y-intercept. The x-intercept would be what makes the whole fraction equal 0, or what just makes the numerator 0. And there's no real number that makes the numerator 0, so there's no x-intercept either. The vertical asymptote is what made the function undefined. We've already identified that as x equals 0. And the horizontal asymptote, you think about the theorem on horizontal asymptotes, the ratio of the leading part, the degree of the numerator is the same as the degree of the denominator. So the ratio of the leading coefficients would just be 1 over 1. The horizontal asymptote is y equals 1. I haven't talked about slant asymptotes yet. There's coming up one on the next example. Right now, we'll just say there are none. By the way, there cannot be both a horizontal asymptote and a slant asymptote. So if there is a horizontal, there's not going to be a slant. All right, the first derivative, you could either take the derivative of this using the quotient rule, or you could take the derivative of this term by term. And if you took the derivative of the second term, that's 0. So I'm just going to take the derivative of 4 over x squared. I'll do my work up here, label the g part. My function is 4 over x squared plus 1. I could write that as 4x to the negative 2 plus 1. And that makes it easy to see the derivative is negative 8x to the negative 3, or negative 8 over x cubed. So the first derivative is negative 8 over x cubed. Critical value of the first derivative would be the values for which the function's defined. That's everything but 0. But the first derivative is either 0 or undefined. Well, there's nothing that makes that fraction equal 0 because the numerator is negative 8. The only thing that makes the fraction undefined is 0, and we already know there's a vertical asymptote there, so it can't be a critical value, and there are no critical values. No critical values tells us that there are not going to be any relative max or relative min. Right, the second derivative, the I part, I'm just going to take the derivative of this negative 8x to the negative 3. That would be positive 24x to the negative 4, or 24 over x to the 4th. And we put that for the I part, 24 over x to the 4th. It has no critical values because nothing makes it 0. And the only thing that makes the fraction undefined is 0, which we already know what happens there. There's a vertical asymptote. So we're ready for our sign chart. And this function's defined for all real numbers except for 0. It goes from negative infinity to infinity, except for 0. And it might be a good idea to put in a dash vertical line at 0 to remind myself there's a vertical asymptote there on the graph. There were no critical values, so I just need to find the sign of each derivative to the left of 0 and to the right of 0. To the left of 0, here's my first derivative. If I put in a negative number, I'm going to have a negative divided by a negative is a positive. And if I put in a positive number into the first derivative, I'm going to have a negative divided by a positive is a negative. Second derivative is not going to be negative no matter what I put in, except for that 0, it's going to be positive everywhere. So that tells me the increasing intervals of this function are where the first derivative is positive. That's negative infinity up to 0. And it's decreasing where the first derivative is negative. That is 0 to infinity. We've already said there are no relative max and min because there are no relative or no critical points of the first derivative. The function is concave up wherever the second derivative is positive. And I would say that's from negative infinity to infinity, except for the functions not defined at 0. So I have to write that concave up as two separate intervals, negative infinity up to 0 and 0 to infinity. There are no intervals over which the function is concave down because there's nowhere the second derivative is negative. And there are no inflection points because there were no critical numbers for the second derivative. All right. I don't have any point to graph. I can graph my vertical asymptote and my horizontal asymptote, but I don't have any intercepts or relative max or min or points of inflection. So I'm just going to graph the vertical asymptote at x equals 0. That's the y-axis. And the horizontal asymptote at y equals 1. Now I'm going to look at my sign chart and say to the left of 0, to the left of that vertical asymptote, the function's supposed to be increasing and concave up. Could that possibly be below the horizontal asymptote? That would be decreasing and concave down, and there would also have to be an x-intercept. We know we don't have any x-intercepts, so no part of this graph is below the x-axis, or excuse me, below the horizontal asymptote. Here's our increasing concave up to the left of 0 and decreasing concave up to the right of 0. Here's decreasing concave up. And then you can check that on your calculator. What do you know about horizontal asymptotes if the degree of the numerator is bigger than the degree of the denominator? Top of the fraction's getting big faster than the bottom. What's true about horizontal asymptotes? There is none. A fraction's not going to have some limiting y value if the top of the fraction's getting big faster than the bottom. However, if the degree of the numerator is just 1 more than the degree of the denominator, something special happens. And that special thing is called a slant asymptote. Slant asymptotes occur when the degree of the numerator is 1 more than the degree of the denominator. And to find the equation of the slant asymptote, you divide the denominator into the numerator. You're dividing, say, an x cubed something into an x to the 4th something. You always get a linear quotient because you're dividing one higher power by one lower power. That linear quotient is the equation of the vertical asymptote, or of the slant asymptote. And on the back of that page, I gave you 3 examples. This is actually from college algebra or from pre-calculus. Case 1, I found that slant asymptote just by breaking the rational expression into 2 fractions. And the linear portion there is just the y equals -1/2 x. So y equals -1/2 x is your slant asymptote. Another word for slant asymptote is oblique asymptote. I usually use the word slant. If you're dividing just by x plus or minus a constant, you can use synthetic division to get your slant asymptote. Again, use synthetic division. That bottom line is your quotient, the coefficients of your quotient and your remainder. So the oblique asymptote would be the linear portion, would be the quotient, y equals 2x plus 3. And if you have something you can't use synthetic division on, you have to use long division. And please Please tell me I didn't ever give you one of those. I don't think I gave you anything you had to do long division on. But if you did, there's long division and your quotient y equals x would be your slant asymptote. Number 20. What's the domain of that function? Everything but -3. What do we know is happening at -3? And what is true about the graph? Okay, so that's where there's a vertical asymptote, x equals -3. How do we find the y-intercept? Let x be 0. When I let x be 0, I just cover up all the terms with an x in it. You get y is -7/3. The x-intercept is always a little bit harder to find. How do you find it? Set the whole thing equal to 0, or with a fraction, you can just set the numerator equal to 0. So the C part, you'd say -x² minus 4x minus 7 equals 0. How could you solve that? Is it going to factor? No, there aren't going to be any factors of 7 that have a sum or a difference of 4, so it's not going to factor. What's my other way to solve a quadratic equation? Quadratic formula, I'm going to put, for time's sake, QF ... It turns out that there are no real solutions to that equation. End up with a negative under the radical. So what does that tell you about x-intercepts? There are no x-intercepts. We already know the vertical asymptote is -3. What does the theorem on horizontal asymptotes tell you about horizontal asymptotes of this function? The degree of the numerator is higher than the degree of the denominator. There are no horizontal asymptotes. But if the degree of the numerator is just 1 more than the degree of the denominator, there's a slant asymptote. And how do you find it? Some kind of division. Synthetic, long division. I hope I never gave you long division. I don't think I did. So let's use synthetic division and label this work my part F. I'm going to divide. What should go in the box? -3. And then the coefficients out beside that, coefficients of the numerator, -1, -4, -7. Do my synthetic division real quickly. And these first 2 numbers are the coefficient of my quotient. So my slant asymptote is y equals what? I'm dividing an x² by an x to the first. That -1 is the coefficient of x. So what's my slant asymptote? -x minus 1. It doesn't include your remainder, just that linear quotient, -x minus 1. Either 0 or undefined. So -3 can't be a critical number. Critical numbers are the zeros of the numerator, -5 and -1. Went ahead and found the second derivative. And notice in the second derivative, the numerator is always negative. The denominator, since that's x plus 3 cubed, the sign of the denominator will depend on the X values that you use for test values. Critical values of the second derivative can't be -3, because we know there's a vertical asymptote at -3. There's nothing that makes it 0. So there are no critical values of the second derivative. And that tells us there are no inflection points. I went ahead and did the sign chart again, just to save time. I think you know how to do that now. Let's get our increasing intervals, looking at the sign of the first derivative. The function is increasing where the first derivative is positive. I don't want to write that interval all the way from -5 to -1 because there's a vertical asymptote at -3. I'm just going to write that interval as -5 to -3. And then from -3 to -1. Decreasing intervals, wherever the first derivative is negative. And that is from -infinity to -5. And from -1 to infinity. The function has a relative max wherever the function goes from increasing to decreasing, and that happened at -1. So the relative max is -1, -2. And there's a relative min wherever the function went from decreasing to increasing. So that happened at -5. And when I put -5 into the original function, I got +6 for the y value. For concavity, I'm going to look at the sign of the second derivative. The function's concave up whenever the second derivative is positive. So that's all the way from -infinity to -3. Hey, I just thought of something that might help you. I thought of it earlier and forgot to mention it. But if I put my vertical asymptote on my number line, I'll make sure not to write an interval, say from -5 to -1. I'll remember there's a vertical asymptote I have to break for there. For my concavity, I can write that all the way from -infinity to -3 because there's no discontinuity between -infinity and up to -3. So the function's concave up from -infinity to -3. And it's concave down from -3 to infinity. If the concavity changes at -3, then why isn't there a point of inflection? We said up here, if there were no critical values of the second derivative, there were going to be no points of inflection. That's because the only place the sign did change for the second derivative already is labeled a vertical asymptote. It can't be a point of inflection. So we will write about no points of inflection. Let's finish this graph. We already have the vertical asymptote at x equals -3. We already have the slant asymptote y equals -x minus 1. And we have the y-intercept at 0, -2 1/3. So what else do we know? Let's look at the sign chart. Oh, let me graph these two other points. The relative max is -1, -2. The relative min is -5, +6. So now let's look at the sign chart. From -infinity up to -5, we know the function is decreasing and concave up. Negative infinity up till this point. Make the graph look, I don't remember if I said increasing or decreasing. I meant decreasing and concave up. So decreasing and concave up to that relative min. And then from that relative min to the vertical asymptote, the graph is increasing and concave up. So there's the left portion of that graph. And then from the vertical asymptote to the relative max, the graph is increasing and concave down. It's from the vertical asymptote to the relative max. The graph is increasing and concave down. And then from the relative max to infinity, the graph is decreasing and concave down. Decreasing, concave down, and approaching that asymptote, because that's what being an asymptote means. The graph keeps getting closer and closer to that diagonal line as x goes to negative infinity or as x goes to positive infinity. We're about to run out of time. So let me just do a couple things right here. I'm gonna plot the point 0, -7/3. 0 and close to, no, a little over -2. It's -2 1/3. My vertical asymptote at -3. And my horizontal my slant asymptote is the line y equals at -x - 1. It has a y-intercept of -1, a slope of -1. So go down 1 over 1. Be right about where that -2 is labeled. And that's my slant asymptote.